Okay, so we're gonna start talking about eigenvalues and eigenvectors. I know that sounds very strange, but they're important when we talk about matrices. Before we get there, however, there's one more thing. Let's talk about solving systems of equations, and which we spent some time on before. But in this case, what we want to focus on is systems of equations where you're looking for a system where both the right side of both equations equals zero. So in matrix form, remember that a system of equations we can write in matrix form by taking our coefficients. So in this case, we would have 2, 3, 4, 5 times xy equals our answers, which would be 0, 0. And remember, we can write this as A, our matrix A times this, we're going to think of as a vector. And yes, this is the time we're going to think of 0, 0 as the zero vector, which is a vector that doesn't go anywhere, right? And in the world of, well, equation solving, we would call this a homogeneous system of equations. So a homogeneous system of equations is an equation where everything's equal to zero rather than non-zero numbers here, which is what we were mostly focused on last time. Now, if you think about it, the only solution to this equation, you could do the math. You could solve for one, maybe solve for y, plug it into the other one. But if you think about it, what's the only numbers that you could do 2 times whatever x is plus 3 times whatever y is and get 0, and also 4 times whatever x is plus 5 times whatever y is and get 0? Don't think too hard. For sure, you have to agree that the only solution to this system is going to be when x is 0 and y is 0, right? Which we could express that if we were working in matrix form, we could express that as x, y equals the zero vector, 0, 0. Okay, and this is often called the trivial solution. If we were applying this to some kind of biology, maybe X was a species of animal and Y was a different species. You know, if we got 0, 0, that would be like saying there's 0 of each species, which is not super interesting. So we usually call this the trivial solution. Yeah. Now, if you think about it, if you solve a homogeneous system like this, where the right-hand side is always 0, 0, 0 would almost always be a solution, right? And one way you can tell that is if the determinant, notice the determinant in this case of my coefficient matrix, let's just do that right up here. My determinant here would be 2 times 5. Remember, we do the product of the main diagonal minus the product of the off diagonal, 3 times 4. 10 minus 12 gives me -2. And the important thing here is that my determinant was not equal to 0. So we will always, if we have a system of equations where your coefficient matrix, the determinant is not equal to 0, then the trivial solution is going to always be what solves that. Now, what would happen though if my system of equations, now notice what I'm doing. I have the first equations the same, 2x plus 3y equals 0. But I made my second equation 4x plus 6y equals 0. My coefficient matrix is now 2, 3, 4, 6 times xy equals 0, 0, the zero vector. And notice this time my determinant is 2 times 6 minus 3 times 4. My determinant is 0 in this case, right? I'm going to separate this out. Now, we talked about before when we were talking about non-homogeneous systems of equations where the right side doesn't equal 0 and 0. if the determinant's equal to 0, on a non-homogeneous system, it could either mean that the lines are parallel or you're really just talking about the same line. Or in other words, there would be no solution or infinite solutions. But on a homogeneous system, if the determinant is equal to 0, there's only one option here, right? If you think about it, these are the same lines, right? The second equation is really just the first equation times 2. So we're talking about the same lines. I'm going to write that here. Same lines. And if these two lines are the same, then we actually are going to have infinite solutions. Okay, so it's if it's a homogeneous system, then if your determinant is equal to 0, it's not they can't be parallel because these have to be 0 here. So it's always going to be a situation where we're talking about these are the same lines, which means they have infinite solutions. Okay. And one way to express, if there's infinite solutions, we ought to be able to find some, right? So one way to express this is if I took, for example, this top equation, if I set 2x plus 3y equal to 0, and let's say I solve for y, move the 2x over, divide by if I move the 2x over and divide by 3, I'm actually going to get y equals negative 2/3 x, aren't I? So scratch that out, negative 2/3 x. Yeah. So for example, let me change my entry value. So if x was 3, for example, if my solution is always y equals negative 2/3 x, I could plug in 3 here and see that my answer for y would be negative 2. And you can tell that if you plug in 3, negative 2 here, you're going to get 6 minus 6 gives you 0. If my x value was, let's change this to 6. If x was 6, y would be negative 2/3 times 6 would end up being negative 4, which is also a solution. And you can do this for any x value. If x was negative 1 and I plug that in here, y would be equal to positive 2/3, etc. Okay, so there's an infinite number of solutions. And if you just solve for y and make it y equals negative 2/3 x, then you can easily find solutions by just choosing different x values. And I guess I would add to that, yes, 0, 0 is a solution to this. If x is 0, y is going to be negative 2/3 times 0, so y would be 0. That is a possible solution, but there's more, right? It's more than just 0, 0. As we saw on the one above, if the determinant of A is not 0, like in the first example, the only solution is 0, 0. Whereas on this one, when the determinant is 0, not only is 0, 0 a solution, there's many more solutions, right? There's an infinite number of solutions. Okay, so we needed to understand that. We're going to come back to that too, so keep that page handy. And now what we're kind of focusing on, what we're interested in here is, if we think of a vector being a 2x1 matrix here, what happens when I multiply a vector by matrices? In this case, it would be, all of these are going to be 2x2 matrices. This is a 2x1, so I know I can multiply them together. So let's just try it. Say I have this matrix 0, negative 1, 1, 0, and I want to multiply it by V, which is negative 6, 1. We know how to multiply matrices, so I'm going to get 0 minus 1. And then for my second number, I'm going to get negative 6 plus 0. So I end up with negative 1, negative 6. So let's think about what just happened here. We multiplied this matrix times our vector V, and we can think of this as another vector. Let me call this vector W. Okay. But let's see what happened. Vector v, negative 6, 1, if I wanted to represent that, that would be a vector that is negative 6 in the x direction, 1 in the y direction. So that vector v might look something like this. When I multiplied v by this matrix, I ended up with the vector negative 1, negative 6, which would be down here. And this is vector w. And you can probably, let me add some lines here. If you think about this as like, to get this vector, I had to go negative 6 up 1. So you could kind of think of this as part of the equation of a line. If I had to think about a slope here, this slope would be negative 1/6, right? Rise over run. But for this vector, you had to go left 1, down 6. This is negative 1, negative 6. What's the slope of, if this was a line, it's positive, rise over run. The slope here is positive 6. So if you remember about perpendicular lines have opposite reciprocal slopes. So these two vectors are actually perpendicular. Also worth noting is, remember the magnitude, if I did the magnitude of v, that's the square root of negative 6 squared plus 1 squared. What is that? The square root of 37. And the magnitude of w, you can tell because I have the same numbers here, is going to be the square root of negative 1 squared plus negative 6 squared is also the square root of 37. So the question just says, what happens? Well, effectively what happened, multiplying matrix A by this original vector V had the effect, one way to describe it is it kept the magnitude the same, right? It preserved the magnitude, but you could talk about it, it actually rotated the vector by 90 degrees. What is this? In the counterclockwise direction, right? This is 90 degrees because it's a right angle. So if I had to describe this, I would say matrix, let's call this matrix A, had the effect of rotating V counterclockwise by 90 degrees, but I'm going to say preserved the magnitude, preserved the magnitude. Means it didn't change the magnitude, right? It kept it the same. So that's interesting, right? Will that happen every time if I multiply a matrix by a vector? Is it always going to just rotate it a certain amount and not change the magnitude? Your instincts maybe are probably telling you that seems pretty, coincidental. And you'd be right there. So let's say I take a different matrix, 1, 8, 2, 3, multiply it by our same original vector, negative 6, 1. Let's see what we get. First row times column gives me negative 6 plus 8 gives me 2. Second row gives me negative 12 plus 3 is negative 9. So if I think of this as A, V gives me a different vector W, let's see. Well, vector V, stop this up. Negative 6, 1 was going off in this direction. We know the magnitude was the square root of 37. Vector W, 2, negative 9 over 2 down 9 would be a vector going off in this direction. So clearly there's been not only a rotation, but if you think about, you could probably figure this out in your head, but what would the magnitude of W be? The square root of 2 squared plus negative 9 squared is the square root of 81 plus 4, the square root of 83, right? That's different than vector v. So what's going on here is what happens more generally is if you take a vector, multiply it by a 2 by 2 matrix, it's going to probably rotate the vector in a certain way and change the magnitude, which is what happened here. So I would say matrix A when multiplied by V. How about I say changed the direction? And the magnitude. Whoops. And I'm just going to put in here, this is what happens most of the time. If you give me a random matrix and I times it by a vector, this is what's going to happen most of the time. It's going to give you a completely different vector. This is what happens most of the time. Okay, so what have we seen here? We've seen what I just said here is, generally speaking, if you take a matrix times a vector, it's going to not only change the direction, it's going to change the length. In some special cases, maybe for a certain type of matrix here, you might just find that your matrix actually just changed the direction of your vector, but didn't change the magnitude, right? So what's the third option? And it turns out that this is the one that we're really going to be paying a lot of attention to. Let's try our vector v on this matrix. 3, 6, negative 1, negative 4. And remember, my vector v was negative 6, 1. Let's see what happens. Negative 18 plus 6 gives me negative 12. 6 minus 4 gives me positive 2. Now, if you look closely, what you might notice is negative 12, 2 happens to be 2 times my original vector. So what we've seen here is A times my vector v, if I go over here, actually gave me 2 times my vector v. So what happened? It didn't change the direction, right? I'm just going to estimate. Here's vector v. When I multiplied my vector v by A, what I got was just double the size of this vector. I think I'm going to have to do this in red. So this red vector was A times v. So notice what happened in this case. A multiplied by v had the effect of changing the magnitude, but not the direction. And as I said, this is the case where we're, strangely enough, and you'll see why later, why we want to focus on this one. This is kind of an interesting thing for us. There's uses for this. Okay. So to summarize what we just learned here, what just happened here was when we multiplied A times V, we ended up getting 2V, right? It doubled the length. Oh, I should have just, this is kind of summarizing what I just wrote here. I didn't read ahead. So multiplying vector V by matrix A had the effect of, how How about we just, okay, I could explain it a different way. Stretching, right? V had a certain magnitude. It was square root of 37, I believe. When we multiplied it by matrix A, it basically stretched out vector V, right? By a factor of 2. Okay. And when this happens, that vector V is called an eigenvector of matrix A. And that 2, that stretching factor, we're going to refer to that as a lambda. Lambda equals 2 is called an eigenvalue of matrix A. And so the questions then are going to be this. Are there more eigenvectors and eigenvalues for my matrix A, right? And if there are, how do we find them? And that's what the rest of this talk's going to be about, is how do we find those eigenvectors and eigenvalues? And the answer to the first question is this. Generally speaking, for a 2x2 matrix, which is mostly what we're going to focus on, there are two. Okay, it gets tedious to write eigenvalues and eigenvectors. So a lot of times I'll write E values and two corresponding eigenvectors. I'm going to put, let me put above this, in general. Mostly for what we're interested in. Okay. So we found one of our, for our matrix A, we know one of the eigenvalues is 2, and we know one of the eigenvectors is, so I'll put 4A equals, what was our matrix? Our matrix was 3, 6, -1, -4. 1 eigenvalue is 2 with, and since we know there's going to be 2, we're going to call that lambda 1, with eigenvector 1 being the -6, 1 that I started with. Right, we saw up above that when I multiply this matrix times that vector, I end up getting 2 times that vector. So this is an eigenvalue. This is the associated eigenvector. But we know there's 2 eigenvalues, generally speaking, for a 2x2 matrix and another eigenvector. So how do we find those? So now we're on to question 2. How do we find those? Well, to do that, let's think about what we were looking for, right? Now that we know what we're searching for a vector V and an eigenvalue lambda, so that if I multiply that matrix A times my special eigenvector, I just get some number, some constant times my vector. I just get a stretching factor times my vector. So this is what we're looking for. Now, if I work with this and I solve it, you don't want to divide out V. That's dangerous even if you're doing algebra. You don't want to divide out variables. So instead, I'm going to move this over. AV minus lambda V. I'm going to factor out of V. I'm going to put that on the right side. So what does that technically leave me with is A minus lambda. Now, the next step might be a little confusing until you realize that A is a matrix and lambda is a constant, a number, right? So this doesn't make any sense. How can you do like a matrix? Let's say it's a 2x2 matrix with 4 numbers -7, let's say. That doesn't make any sense. You can't subtract a matrix, a constant from a matrix, right? That doesn't make any sense. But I can make this make sense if I do this. If I multiply lambda by, remember we talked about this, the identity matrix is like the matrix equivalent of 1. Now what I have is a matrix and lambda times I is a matrix. These are both matrices, right? So now I have a matrix minus a matrix, which I can do. And a matrix minus a matrix is going to be another matrix. So this is going to be a matrix times V equals 0. And to really emphasize this, I'm going to put 0 like as if it's a vector. That should look familiar. That should look familiar because back at the beginning, we saw that when we have a matrix times a vector equals 0, there's two possibilities. One of them is if the determinant of A is not equal to 0, you're just going to get the trivial solution. That's not very interesting. What we want to do is have non-zero answers if possible. So we're more interested in the non-trivial solution, which we know will happen if the determinant of, where is it? No, right here. If the determinant of A equals 0, then I have infinite solutions, which is better than 0 and 0 as my only solution. So this is what we're really interested in. So that's what this next part is. We know that the non-trivial, the non-zero solution to this type of an equation is going to happen when the determinant of this is a matrix, equals 0. And so what am I taking the determinant of? I'm taking the determinant of A minus lambda times I. If that equals 0, then I'm going to get some non-trivial solutions. Okay, so let's see how that works. My original matrix A was 3, 6, -1, -4, minus lambda times I. In this case, since we're doing a 2 by 2, we would be doing a 2 by 2 I matrix equals 0. We know that if this is a constant, you can just distribute the constant into each part there. So lambda minus lambda times 1 is going to give me, well, it's already got a minus there. So it's going to be minus lambda. I'm going to leave the minus there. Lambda times 0 is 0. Lambda times 0 is 0. Lambda times 1 is lambda. And we know that if I've got, as long as I have the same dimensions, 2 by 2 minus a 2 by 2, I can just subtract in the correct position. So for my upper left, that's going to be 3 minus lambda. 6 minus 0 is 6. -1 minus 0 is -1. -4 minus lambda is going to be this entry. So in this case, I will get non-trivial solutions whenever the determinant of this is equal to 0. So let's find that determinant. Determinant is main diagonal multiplied minus the product of the off diagonal, which is 6 times -1 equals 0. This gives me -12 minus 3 lambda plus 4 lambda. Negative lambda times negative lambda is plus lambda squared. Minus -6 is really plus 6. This looks like a quadratic that I could probably factor or at least use the quadratic formula on if it doesn't. So let's put the lambda squared first. -3 plus 4 lambda gives me positive lambda. -12 plus 6 is -6. And if I factor this, what am I going to have? +3 minus 2. So I get two possible values for lambda. Lambda equals -3 or lambda equals from this one 2. Now remember, this is all going back to that same problem we started with, right? When we multiplied our matrix times -6, 1, we found that our we ended up getting twice that vector. So we decided one of our eigenvalues was going to be 2. And there it is, right there. So that was expected. We already knew this one. So, and I think we call that lambda 1. So we'll leave that. And let's call this is going to be our second eigenvalue. Now, technically, we already know the eigenvector that goes along with 2. If you go back to what we learned up here on page 2 here, when we multiplied our matrix A times -6, 1, we got 2 times -6, 1. That's our eigenvalue, and this is the eigenvector that goes with it. So we already know the eigenvector that goes with 2 is going to be -6, 1. But let's pretend we didn't know that. I'm going to show you how you can figure these out. So let's pretend we didn't know that. If I wanted to find my eigenvectors, let's start with lambda 1 equals 2. There's a couple of different methods that get taught. My favorite, though, I want students to go back to the definition and remember what an eigenvalue really is. What an eigenvalue really is if I take my matrix, no, it was 3 here. This was a 3. 3, 6, -1, -4, and multiply it by whatever this special eigenvector is. I'll call it xy. I'm going to get my eigenvalue times that vector. So here you see a little bit of insight into what is the value of an eigenvalue. Why is that important? Because compare the equation. What this is saying is a matrix times xy is the same as a number times xy. So do you see that the real, and this is what we're going to exploit later on, the real coolness of an eigenvalue is it allows you to take this whole matrix times xy can be boiled down to just a number times xy, right? So an eigenvalue in some ways has the ability to replace a matrix, a whole entire matrix, with just a constant, with just a number, right? So that's the really cool thing about eigenvalues. Anyhow, to find the eigenvector, here's what we're going to do. Since this is an equation, if we multiply out the first row times the column, 3x plus 6y, that should have equaled the top number here, which would be basically 2 times x. If I just even work with this, I know there's a second multiplication I could do, but if I just work with this, check this out. If I subtract the 2x over here and move the 6y over there, this is really all I need to find my vector, a relationship between x and y. Because what this says is for my vector, which is going to be x and y, whatever y is, x is going to be -6 times y. So if I simply just choose, I think the easiest thing to be would be just to choose y to be 1, then x would have to be -6 times 1, which is -6. And if you go back, that's exactly what we saw, right? I'm going back to page 2 again. When I multiplied that matrix by -6, 1, I ended up getting 2 times -6, 1. So that is my eigenvector. That's my eigenvalue. And that's exactly what I got here. Now remember, we had another eigenvalue. Our other eigenvalue was -3. So let's find the corresponding eigenvector. And we'll just do it the same way. We're going to multiply our matrix times our eigenvector, which is going to be different. It's not going to be the same as this one, should equal my eigenvalue times the vector. If I multiply out this, the first row, 3x plus 6y should equal the top number here, which is -3x. And I can actually, this is all I need. If I move the x's over here and move the y over there and divide by 6, I end up with this relation. And again, that's all I need. So one of the questions I get all the time is, what about the second multiplication? How come you didn't multiply this by this? There's times I might need to do that, but oftentimes if I just multiply the first row times the column and set it equal to this top number, if I can get a relationship between x and y, that's really all I need. Because what I would do here, if x is equal to negative y, I would just say, well, why don't we, let's just let y be 1 then. If y is 1, then x has to be negative 1. So that is the eigenvector for this eigenvalue. And like I said, for a 2x2 matrix, generally speaking, every 2x2 matrix will have 2 eigenvalues and 2 eigenvectors. So now we spent a lot of time on that one. Let's start from the beginning. Here's a new matrix. And what you should be able to do is find the eigenvalues and the associated eigenvectors. What we've learned is to find the eigenvalues, we want to have the determinant of, I'm not going to go through the whole thing. I did that backwards. A minus lambda times I come out to be 0. And what I want to share with you is, going back to how we did it here, A minus lambda I. Can you see that if I always have lambda I, the main diagonal entries, if those are 1 and 1, because that's I, and I get multiplied by lambda here, and then I do the subtraction, what it's always going to boil down to is the 2 main diagonal entries always just get a minus lambda, and the off diagonal entries just stay the same. And then you just set that determinant equal to 0. So that's kind of the quick way to do this. So this is going to turn into the determinant of -4 minus lambda, 1 minus lambda. So the main diagonal entries get a minus lambda, and then the off diagonals just stay the same. The determinant would be -4 minus lambda, 1 minus lambda, minus the product of the main diagonal, which is -6. Now, the other thing is that what I usually do here is, you're anticipating you're going to end up with a quadratic to factor. So I usually, knowing that I usually want my lambda squared to be the beginning, I foil this out kind of backwards. Negative lambda times negative lambda is going to give me my lambda squared. This is going to give me +4 lambda minus lambda for these two, -4 plus 6. That's +3 lambda. -4 plus 6 is +2. And this factors into lambda plus 1, lambda plus 2. So my 2 eigenvalues for this matrix are -1 and -2. Those are the only 2 possible eigenvalues for this matrix. So now what I need to do is find the corresponding eigenvectors. Every eigenvalue has a corresponding eigenvector. So to find, and we'll just arbitrarily, it doesn't matter which one you do. Let's call lambda 1 equals -1. And what you're always going to do is use the definition. My matrix times the vector I'm looking for is equal to lambda times my vector. So I have -4, 2, -3, 1 times a random vector equals -1 times my random vector. Multiply out. -4x plus 2y equals the top number here, since I did the first row times the column. And I think I can get a relationship out of that, so I won't have to bother with the second row. It doesn't matter how you solve this. Like I kind of want to have my x's positive. So I think in this case, I'm going to add the 4x over here. 2y is equal to 3x. So maybe I solve for y. Y is equal to 3/2 x. Okay, so let's talk about this. As you saw in the previous one, what I will then do with this is to find a vector is I will choose a value. Now, in this case, since y is written in terms of x, what I want to do is choose a value for x. Choose. Now, it's certainly fine. If I let x be 1, then y would obviously be 3/2. But I try not, you'll see there's a time when you really try to avoid having fractions if you can. It's totally fine. If you choose 1 and y is 3/2, that's totally fine. Oh, one other thing is, yes, of course, if you let x be 0, y would be 0. But if you did that, that would give you the trivial vector, right? And we don't really want that. We want to stay away from 0, 0. So if I want to avoid fractions, what would be a better number to plug in for x? How about 2? If x is 2, y will be 3/2 times 2, which is 3. Okay. I should mention this on this point. It's not, again, if you choose 1 for x and you get 3/2 for y, that's fine. If you chose, let's say you chose 4 for x, and if 3/2 times 4 would give you 6, these are all fine as well. And the way, if you think, here's what it really comes down to. If you were to plot any one of these vectors, maybe I use a different color here. 2, 3 is a vector that goes over 2, up 3, over 2, up 3. So that might look like this. 4, 6, you probably recognize is just an extension of that, right? That's just double that vector. 1 3/2 is over 1 3/2. That would actually be going in the same direction. So all of these are fine because they really are just vectors that are pointing in the same direction. But this is probably the one that your textbook's going to probably go with because it doesn't involve fractions and it's simpler than 4, 6. All right, we have one other eigenvalue. And that one was -2. So I'm going to take my matrix times a vector equals my eigenvalue times my vector. -4x plus 2y equals -2x. If I add 4x over here, divide by 2, I end up getting a nice relationship, y equals x. And the simplest vector that where y and x are both the same, I think would just be to choose them both to be 1 and 1. Let's do one more and then we'll be done here. And if you want, this would be a good time. This would be like a good practice problem. Pause the video, set up your formula to find your eigenvalue. And you could even try your eigenvectors. A minus lambda I is going to really be the determinant of, as we've seen, main diagonals get the minus lambda, off diagonals stay the same, and we want that determinant to equal 0. My determinant would be 3 minus lambda times 4 minus lambda minus the product of the off diagonal, but 1 times 0 is just 0. And look, in this case, look what happens is if that's 0, there's no reason to FOIL this out. That means I have this times this equals 0. I can see my eigenvalues right away. And in fact, I did this intentionally. if you go back and look at this, can you see that these eigenvalues are just these two numbers here? And why did it work out that way? It was really because this product came out to be 0, right? You did this times this, and then this came out to be 0. So the way it works is if one or both, if this one was a 0 and this was a 1, the same thing would have happened, or if they were both zeros. If you're off diagonal entries, if one or both of them is equal to 0, then these are your eigenvalues. That's worth noting. And that's actually a nice shortcut. It's not cheating. It's a good thing to know. So I'll put if one or both of off diagonals is 0, then the main diagonals are your lambdas. They are literally your lambdas. And if that's the case, if you see that in the future, if you see one of these as 0, you can skip this and just say right away, my lambdas are 3 and 4. And that's a nice shortcut. Okay, so now let's find our eigenvectors. We'll just randomly call lambda 1 equal to 3. Matrix times vector equals eigenvalue times vector. 3x plus 1y would actually have to equal 3x, huh? Now, in this case, the only way that could happen is if y equals 0. Now, okay, this is kind of cool. I'm glad this came up. But notice it didn't say anything about what x had to be, right? Well, let's go down to the second row. We haven't done that yet. What does the second row times the column tell me? It says 0x plus 4y equals the bottom entry, 3y. Now, if 4y equals 3y, that also leads me to the same conclusion, that y would have to be 0. So when this happens, if it was x equals 0, it'd be the same story. If you get y equals 0 here and it doesn't say anything about x, what that means is x can equal anything, any number. It's just the only requirement is y has to be 0. So if that's the case, then what would I choose for my eigenvector? I know my y has to be 0. If x can be any number, again, you don't want to use 0. That would be 0, 0. The simplest number would be to choose 1. My eigenvector is 1, 0. One more. Matrix times vector equals eigenvalue times vector. 3x plus y equals 4x. I think this one's going to be nice. That just tells me once again that y is x. So my second eigenvector I would just choose as 1, 1. Okay. So yeah, I know that we haven't really talked about why is any of this useful, but trust me, this is going to be very, very useful, not only in 17b, but especially in 17c. We're going to be doing eigenvalues and eigenvectors a lot next quarter. All right, hopefully this was helpful.